email to remind me. I'll update it. Yeah. Okay. Okay, so now we're here. We've studied all the individual thingies, from rubble, planets, comets, terrestrial planets, Jovian planets, things that we didn't know existed, like super-Jupiters and mini Neptunes, and then stars, stellar remnants, and then how they interact in cities of stars, clusters, and galaxies. So now we're doing cosmology, which is like the history of the whole thing. First, really quickly, just what cosmology takes into its scope of study, and then we'll get to Hubble's law and the Big Bang, and then on Friday we'll finish with the shape of the universe and dark energy, which is not dark matter, and just where that leaves us. And it's a kind of funny way to end a class where you don't stop and pat yourself on the back and say, look at all you've learned. You kind of stop and say, look how little we know now as of 2001, but whatever. That's astronomy. So maybe the 30th time we've seen this. So we've gotten through all of this, and now we're here. So the background of the slide and what's going on with the entire set of things. And at this point, we really only care about galaxies in the sense that they're like kind of the light posts of the cosmos, and we want to just use them as a tracer of matter. So cosmology itself is the study of the universe in general in the broadest sense, both its history and its contents. And we've kind of got the contents part down. So now it's really, have they always been there? Just to indicate that this is not like a new designation, cosmology has been a component of every single culture. You can't find one that doesn't have these two things. One is a description of what's going on in the cosmos, and then secondly, a creation myth. And you have the same annoying questions in every single one of them. So maybe you have a Vedic cosmology and you think there are 7 stages of animate matter, and then somebody says, where do they live? They all live on Earth. And then you ask, well, what is Earth riding on? Well, what must be strong enough to carry the Earth through the cosmos? Not to turtles yet, 4 elephants. And then you ask, well, what's strong enough to have 4 elephants standing on its back? Turtle, very giant space turtle. And then you say, well, what's a turtle standing on?
Turtles all the way.
Yeah, one answer is turtles all the way down, which is the modern answer is that it's infinite. But the alternate answer is a big scary snake. Stop asking questions. And then this is the first one that we got to, is that the Ptolemaic and the Copernican models both, honestly, it didn't matter if you put the sun or the earth at the center, is that the cosmology was this very kind of creepy prison cosmology where the set of things that the universe contained was a bunch of crystal spheres, and they're perfectly spun, and then on the 4th day of creation, I don't know which one, is they were all spun at their particular rate. And then once you got out here, I guess you're, that's it. You hang out with some deity or something like that. So that was everything that there was to be. Once you get to that last sphere, there's nothing left. You get in trouble. That's where Eden is, I don't know. And if you count up the generations in the Bible, you get that this was created 6,000 years ago on October 22nd or something like that. So that is a cosmology. It has the 2 questions we're going to ask, when and what. The Newtonian cosmology was the first one to introduce infinity, and they thought they were being clever. So you come up with Newton's laws of motion, and you basically set everything into clockwork. There are these things called orreries. There's actually a huge one in the seacoast of the Netherlands that this woman built in her home to prove to the Pope that his calendar was wrong, is that you actually set the universe into motion with machine-like gears. And you can actually do this with machine-like gears, and you can correctly predict things, so you don't need a book to do it. So the Newtonian cosmology kind of indicates is that there was a moment of creation, or there was some creative influence or not, and then after that, no intervention required. So Newton's laws take over. It's very machine-like. And further, when people got into the philosophy of it, there was an idea that, well, it could have always been doing this. I don't see why Earth doesn't seem to be losing any energy. It could be orbiting the sun forever. And I could also envision that I've got a star over here. It's pulling the sun to the left. I've got a star over here. It's pulling the sun to the right. What would be true if somebody was pulling on all of your belt loops at once? Would you go left or right or forward or back? It'd be stationary. So Newton even got this one wrong. It turns out that's not true, is that if everything's pulling on everything's belt loops, everything collapses. But there was an incorrect idea that there was this clockwork universe and it could be infinite. But anyway, we still have the same two questions. We're just going to, use math and observation to do it, and not necessarily create the universe out of a, lotus flower or something like that. So this is where we'll start, and we'll just kind of consider the problems of having the clockwork mathematical universe. Doesn't seem to be a problem. I mean, that's nice. It's parsimonious. We don't have to include extra things. But the infinity was a problem, and that's the first thing we'll talk about and get to the Big Bang, is that infinite in time actually isn't the right answer. And people went through all these conniptions to get these infinite in time universes. So the first problem is what's called Olbers Paradox. So if we had a Newtonian infinitely big, infinitely old universe, there's an issue. This is a fake star field, but pretend it's a star field. That's our sun, and there are other suns, other stars. If the universe was infinitely big, should there be a star in this direction? Yeah, there should be a star there where I point. What about there? Yeah, anywhere I point, there should be, go far enough, and there should be a star there. If the universe is infinitely old, has the light had enough time to get to me? Yeah. If the universe is infinitely big and infinitely old, what should I actually see when I look out at the night sky? Everything light. So this is what's called Olbers Paradox, is that this can't quite be right, because what I would see is this, and that would be very terrible. So stars everywhere. And this is a very old and very serious issue with that type of universe. There's a philosophical problem that's not really a problem, it's just something that's kind of fun to think about, is that if the universe is infinitely big, you actually run out of different combinations of matter and you start repeating stuff. Let's just say that there are 27 people in this room, and I ask you all to write down a random letter from the English alphabet. What do I know has happened? Yeah. So one of those letters, every two people must have repeated a letter, which you don't really care about too much. But now let's start getting weird about it, is that there's only a finite way of stacking things like calcium and hydrogen. So at some point I'll run into two identical configurations of matter. And if the radius, is bigger, then I run into bigger identical configurations of matter. So somewhere within some radius that we could, define and find the number for, there are two totally repeated star systems down to the planets. Same weather on the planets, same stars, same masses. Okay, you could get in a bigger radius, and there must be two totally repeated galaxies. This is very unsettling on some level. It doesn't violate any physics laws, but people are like, I don't like this. I want to pretend that I'm a special snowflake. A repeated version of me somewhere in the cosmos of infinity is big. So it must be true. It's guaranteed to be true. So there must be repeats. Okay. So, we'll just skip. So this is... No, we can't really talk too much about the idea of parallel universes. They kind of come in two flavors. They're the string theory version, which is like we just see 3 dimensions. There are 4 other dimensions out there with their own laws, and they split off at some point. And then there's the quantum mechanics version of the multiverse, which is every time you flip a coin, the universe splits into 2 universes, one in which the coin was heads, the other in which it was tails. It's got to be like a quantum mechanical coin, but that's the so-called multiverse. But this is just in a normal, plain old ordinary, no string theory, no quantum mechanical, infinite universe. Okay. So we have a cosmic version or non-version of Olbers Paradox, is that I seem to see an end, right? But this is cheating because this is a lot of technology that people didn't have in Newton's day. So we'll start with the historical argument is this guy again, and this is really why Hubble is famous, is that Hubble, and this is the iconic image in his work boots. It's actually somebody else who took a lot of his really good images. So this is a old school photographic plate. You would look through it, but really it would just take these long exposure photographic plates of what used to be a very dark suburb of what's now a very bright suburb of Los Angeles, a 100-inch mirror So this would be like a 2-meter class telescope. And he started with a very pedestrian question, which was, after proving that the Andromeda Galaxy was outside of our own, he wanted to know how big spiral galaxies were. So if you could, put like a size on them. And painstakingly, what you do is you look for variable stars. So if I find some variable stars there and some variable stars there, I can figure out the overall size. And once I find a couple of sizes of spiral galaxies and I can claim they all look alike, I could just use their overall luminosity. Raise your hand if you think how big spiral galaxies are and are they all the same size is the most interesting question you've ever asked in your life. That's what I thought. So there's a story there in the sense that what seems to be uninspired question turned out to be really, really, really important. And in the course of Hubble using his variable stars, which can now get us outside of our own galaxy again, where is it? There's the variable star in a cluster. So this is a globular cluster in our own galaxy. So this is far enough down the distance ladder that you can actually painstakingly observe individual stars in close-by galaxies. So using this, what Hubble was able to do is say, actually, it's quite true that if you look at a spiral galaxy like us or Andromeda, is that they all seem to be about the same size. And that same size, about 22 kiloparsecs, 75 or so thousand light years. I don't think this is Hubble's original measurement. These were all wrong by like a factor of 2 because of dust, but I think it's pretty modern. So spiral galaxies, most of the stars are contained within of a particular type are contained within about 71,000 light years. You guys aren't cheering? Okay. So this is why this turns out to be really important, is that when I show you a picture like this, which is the nearest telephone pole and which is the farthest? This is the nearest, right? And that's the farthest. How do you know? What are you assuming, actually? That they were all made in the telephone pole factory and they're all actually the same size, right? So again, this is an intuition that you have for a normal human picture that you have to work for in the cosmos, right? So if you know that all of these, stated another way, is you guys know that telephone poles actually should all be the same size, or power lines, whatever they happen to be. So if one appears smaller, then it actually is smaller. So what do you get to do once you painstakingly show that all spiral galaxies of a particular type are actually the same size? Yes. So now what you get to do is if a spiral galaxy appears smaller, it actually is smaller. And the geometry of how you do that is something that you learn in middle school. It just has to do with right triangles, opposites, and hypotenuses. And now Hubble can not use a single star excruciatingly to determine a distance. Now what he has is what you would call like a standard ruler. So you have a bunch of like meter sticks set out in a football field, and you can use the apparent size of the meter stick to tell you how far you are down the football field. And this works as long as you see a spiral galaxy. A spiral galaxy has hundreds of billions of stars in it. So this is very, very, very useful thing to have. And the original paper, Hubble was like, I see the spiral galaxy, it's really small, this is the farthest one I see, therefore the universe must be at least this big. And then 2 days later, or something like that, he saw a different spiral galaxy, and over the course of, a year, the size of the universe, as far as humanity knew it, increased by something like 30-fold. So that's why it's kind of useful. And that's nice. So what Hubble was able to show is, the universe is really big. Which in and of itself is kind of neat. So everybody went, ooh. Now what? So here are a couple of spiral galaxies of that particular type. Which one's closer? Which one's farther? Yeah, know it, because I know that they're actually the same size. You would have probably assumed that otherwise, but scientifically we'd need to put the work in. So now we're stuck, and we have nothing to do. So what do you suppose Hubble did next? What does an astronomer do when they're stuck? Doesn't know what to do? Spectra. What do you think the spectra of a galaxy looks like? So they look like this. They actually have a lot of emission lines in them because there's a lot of hot gas, especially spiral galaxies like this. And there's a lot of hot radiated hydrogen. So in particular, there's this famous hydrogen line. This is where the hydrogen line would appear in the lab, 656 nanometers. And this is the hydrogen emission line in this galaxy. This is where the hydrogen emission line would appear in the lab, 656 nanometers. This is where the hydrogen emission line appears in this galaxy. Looks like there's some discrepancy. So what's going on? Yeah, so this hydrogen alpha line's wavelength is much longer than you would see in the lab. So this is redshifted. So what's going on with this galaxy? It's moving away from us. And in fact, this one, if you were to trace it down, this one's actually moving away from us a little bit too, just a little bit. Okay, so now I can determine that galaxies are moving, and they're moving fast, as it turns out. So this galaxy moving away from us a little bit, this galaxy moving away from us a little bit. And it turns out that every galaxy that Hubble saw, they were all moving away from us. So it wasn't like a random, kind of hive of bees motions. Everything was running away, which is kind of bizarre. And in fact, the smaller they were, which is to say the farther they were away from us, the faster they were running away. And so he sucked it up and did the thing that astronomers hate doing and did maths. And he plotted the distance to the galaxy, which you could just tell from the apparent size, versus the redshift of the galaxy, which is basically how, always redshifted, how fast it's moving away from us because it's Doppler shifted always to the red. And, oh, thank God, it's a nice straight line. Although it's pretty unsettling. It's the easiest piece of math that you'll ever see, is that the speed with which the galaxy is receding away from us is directly proportional, constant, called Hubble's constant. It's not really constant, but forget that for now. Don't worry about it. Times the distance. So basically, if you double the distance to a galaxy, it's moving away twice as fast. If a galaxy is 3 times as far away as another one, it's moving away 3 times as fast. Okay, so what did the Milky Way galaxy do? Why is everything running away from us? So people at first a little bit upset by this because it seems to revive this pre-Copernican idea that there's something special about the Milky Way galaxy. It's like we're at the center. Not only are we at the center of the universe, but we didn't shower, and now everybody's running away from us. It's terrible. So it turns out that, and this is what we'll do starting on Friday, is that if you were to take these same measurements from a different galaxy here, you would see the exact same thing. So if this galaxy is moving away from the Milky Way, what does the Milky Way look like it's doing from this galaxy? Moving away. And if you were to look at this thing, because of the proportionality, the fact that you double the distance, double the speed, if you were to actually look at what this galaxy would see, it would see the same thing. So it's just this observing effect coming from the fact that what's really going on is apparently everything is moving away from everything. So it's as if you took a rubber sheet and you painted a bunch of dots on it, and everybody just pulled the corners, and everything's flying apart. So the entire universe is expanding, apparently. Which means that if you were to play this movie backwards, in the past, what was true about all of these galaxies? Well, they got a little closer, and then you play the movie back a little bit more, they're a little bit closer, and at some finite time in the past, so we got the time problem just about solved, at some finite time in the past, what must be true is that all matter was sitting on top of all other matter. And with his math and his measurement of the constant, Hubble was able to say, it's got to be 10 billion years in the past. It was not the current number. You mean within some radius they don't do it? So that's actually exactly what happens. So within our local group, there's no Hubble expansion. In fact, remember, Andromeda is coming right for us. But that's because our gravity is stronger than the so-called Hubble expansion. So when we're talking about these galaxies, they're all outside of our local group. So we're talking about things that are, a billion light years away, 500 million light years away, things like that. I think Hubble's original data was centered on just under 1 billion light years away, which is impressive. Question?
It's not like everything couldn't possibly be away from itself. So stuff like unless you're making something basis.
Yes, the description that new space is being made is the thing that particle physicists are just.
Made is the word.
No, because every day a particle physicist loses a year of their life worrying about this. I think is that as you're, for one thing, just imagine that you have like a rubber band or something, and then you stretch it, and it seems to be the case is all of the dots, if you put dots on the rubber band, they all seem to move away from all of the other ones. You're not really making new rubber band, you're just kind of stretching things. And to a normal classical physicist, this isn't really a problem because making new space is making new nothing. So I don't really care. But if you're really making space, space actually has some vacuum energy, and there's particles and antiparticles. And those people never get the right answer, and it ruins all their theories, actually. And this is also an English language thing, is that what we really mean is that the average distance in between galaxies is increasing every second. That doesn't quite have the same flair as saying everything's moving away from everything else. Okay, there's a second problem, is that it's hard to make this thing jive with finite space, right? So to say that you bake a muffin and the muffin increases in size, eventually it's going to run out of the oven. So you've got that problem. But we're not there yet, so maybe we can dodge it. And we'll get back to that, actually, in the shape of space. But the prediction was from Hubble's law is that you run this movie backwards, and everything's moving closer and closer and closer. And at some finite point in the past, you get the so-called, and the first time this word was used, it was used completely derisively. It was sneering epithet. It's, the Big Bang, this Hubble guy. And he was actually pretty careful not to say, I believe this happened, but there was a strong prediction that at some point in the finite past, the universe had a beginning. So obviously, this is some form of explosion. It didn't happen at one particular location. It was everywhere. Everything was sitting on top of everything else. So there's no place where the Big Bang occurred where you can go and take a vacation and do some tourism. It's everything. So the entire universe just had zero average distance in between particles. So this obviously has some form of physical prediction that, 10, now we know it's 13.7 billion years ago, everything was really, really, really hot. So these guys came along, and I guess if you heard Fabio's talk, he mentioned it a little bit, but I'll recap, is that these guys were not astronomers, they were physicists, they were microwave antenna physicists, and they got called in, or they were doing some observations with this microwave antenna, and it was trying to, communicate with a communications satellite, basically a big ball of tinfoil in the sky. And they got this hiss from everywhere else. And no matter where they pointed their microwave antenna, they got a hiss. And they even went so far as they thought there was pigeon shit throwing off their circuitry, so they had a graduate student clean out the pigeon shit, and they kept seeing this signal everywhere in space. So they pretended that they were astronomers for about 2 days, and what did they do? They took a spectra. This is their spectra. What kind of spectra is this? So this is wavelength and intensity. Is it absorption, emission, or black body? So just so happens it's in microwaves, but it is a black body spectrum that you couldn't even make in a laboratory. It's so perfect. And it says the entire universe is 2.7 degrees above absolute zero, which agrees with the prediction that came out in a couple of papers, actually just down the road at Princeton, that said if there was a Big Bang and you let it expand for 10 billion years or so, you should get a 5-degree black body temperature everywhere. So this is physical evidence that the Big Bang did occur. It occurred at the right time, predicted by Hubble's law. And so these guys got a couple of Nobel Prizes. Okay. So this is where we'll stop. There's a second question associated with this, is we need to fix this image in your head of the universe is a box of galaxies, and then everybody grabs a corner of the box and stretches it. So this isn't what's going on at all. So you can't go to the edge and push your friend out of the edge of the universe like the Ptolemaic and Copernican people may have thought. What's really true is that general relativity has the answer for us, and the universe is bent around in some way, so we can actually hide the edges of the universe if we have enough matter, or we can't if we don't. So this is we'll do Hubble's Law Lab and then finish up with the curvature and acceleration of the universe. Okay. And then the quiz will be up, and you guys can take it on Friday afternoon. So.